Yep, it's going.
Okay. Yeah, well, thank you very much for the invitation. This is my first time giving an online seminar talk, so kind of a fun thing to try out. Yeah, and I will say, by the way, so I'm going to talk about the Shapiro-Shapiro conjecture. This is joint work with Kevin Prabhu. We were working on it last year. So I do want to start by telling you what the Shapiro-Shapiro conjecture is, but there are a few different statements out there. So it's possible that if you talk to Maria, she will tell you a different equivalent version. So I'm going to talk about it in the context of curves to begin with. So parametric curves. So let's say that we have a curve. A parametric curve is a map from P1 into projective space. And concretely, we're going to imagine that we just picked some polynomials, f sub I of t in one variable of degree at most n. And given those polynomials, they trace out a curve for us in k-dimensional projective space. So in this context, the Shapiro-Shapiro conjecture will have to do with Wronskians. So what is the Wronskian of these polynomials? It's this determinant that I've written down here, where we make a square matrix where in the top row, we just have b of t, f0, f1 up to fk. In the second row, we have phi prime of t, which is giving us kind of the tangent direction to our curve, phi double prime of t, so that's the second derivative, and so on. And we go, I forget if I indexed this correctly, but we go far enough to get a square matrix. I think it might actually, is it? I guess it's, okay, it's k, great. So phi k of t. The other day I thought it was k minus 1, which anyway. So we make this matrix and we take its determinant and we set that equal, well, we're going to think about what this Wronskian is telling us, which concretely, we're going to think about when the Wronskian is 0. So it turns out that this is detecting something in the geometry of the curve, which is a flex, which would mean a value of t such that these vectors, the point, the tangent direction and second derivative and so on, are linearly dependent. That would make this matrix have determinant 0. And a simple example of that would be something like an inflection point. Here, I'm going to sketch it, where we have our point, we have a tangent direction, but then the second derivative would be 0. And that would mean in this context that in this example, we'd have a whole row of zeros. B double prime would be 0. So that's one example of a flex. That's why we call them that, same root word. But it also includes things like cusps, where the first derivative is vanishing, and sort of higher order flexes, and so on. In general, the kind of simple flex, the simplest kind of flex in k dimensions would be one where the first several derivatives are all kind of fine. They're all different directions, but the last one is linearly dependent. That's called a simple flex. Okay, and I'll just point out, I'll just mention in passing that you may have seen Wronskians in differential equations. They sometimes come up there because people use them as a way of testing linear dependency of functions. And so there's actually one case here where this determinant vanishes identically, which would be if these polynomials, f0 through fk, are linearly dependent as polynomials. That would mean that this whole matrix, that there's some, f0 is equal to fk, for example. Then this matrix would have determinant that is identically 0. And this is equivalent to saying that the curve lies in a hyperplane. And we're kind of going to just assume that doesn't happen. That's kind of an easy thing to test. And well, I said this comes up in differential equations because Wronskians in differential equations are used as a way of showing that different solutions to a differential equation are actually linearly independent by calculating the Wronskian and working with it. So there's some connections to places outside of geometry as well. Okay, so Wronskians. I want to show you a couple of examples, starting with a picture of what a higher order flex looks like. So this is in P3. And so I've drawn this space curve, and I've tried to make it look like it's really kind of flattening out into a plane at that point. So what's going on in this picture is that the tangent line is actually kind of perfectly normal. The curve is meeting its tangent line to order 2, which is actually just the standard amount to meet a tangent line. So there's nothing special there. But it's meeting the tangent plane to order 4, which is 1 higher than normal. And so somehow it fits with the fact that this looks planar at that point. The space curve looks like it's in a plane. at that one point. So that's kind of how to visualize what these fluxes are. But you can see that there's a bunch of different possibilities for what a flux could look like. This is just a simple flux. Okay. Cool. And then there's one other core example that has to do with the kind of classical instance of looking at Wronskians. And so that's especially for maps from P1 to P1. So the case K equals 1. So in this case, we don't really have a curve in projective space. We have a map from P1 to itself. And this is really, properly speaking, a rational function. We have a rational function in one variable. So I've written an example here. You'll notice that it has some complex numbers in it, and I'll tell you why I picked this example in a moment. But just to sound out how to think of this as a rational function, this is in homogeneous coordinates. So we can divide through we can divide our homogeneous coordinates by the same thing. So instead of writing it as a polynomial and another polynomial, we're going to divide and write it as this ratio here with a 1 on the other side. And so this map from P1 to itself, if you think of it as a rational function of one variable, it just means this ratio here, t cubed plus, okay, I mean this formula with t in it. And so classically, so what is the Wronskian telling us in terms of rational functions? It actually has a simpler interpretation. The Wronskian of this map from P1 to itself is finding the critical points of this rational function where phi prime equals 0. And you can actually see that directly from writing out the Wronskian. So the Wronskian is this determinant, f0 and f1, f0 prime and f1 prime. And this is, I mean, if you write out this determinant, it's giving you the quotient rule, f0, f1 prime minus f. So setting this equal to 0 is finding the points where the derivative vanishes. And you can see that it has a very nice, the Wronskian is 1 minus t to the 4. So that's why I picked this example, because it's kind of a nice example. The critical points are exactly the fourth roots of unity. So plus or minus 1 and plus or minus I. Okay, so critical points of rational functions. One thing I want to point out, the other reason why I think this example is interesting, is that we started with something working over C. This rational function involved complex numbers, excuse me. But the critical points we got were a mixture of real and complex critical points. And I'm pointing this out because the Shapiro-Shapiro conjecture will have to do with real and complex valued points in algebraic geometry. And like there's kind of a, I don't know, there's a bunch, and all the different possibilities can happen here. If we start with the rational function defined over R, then at the end we still have to solve some polynomial. And so even if we start with something that started out as real, we may get a mixture of real and complex points. Yes.
Could I just ask, so you said you picked this example because the Wronskian turned out to be 1 minus t to the 4th. Did you like jerry-rig it backwards? Is there like a method for creating, functions that have a given Wronskian?
Oh yeah, well actually, you know what, okay. Yes, here, you're gonna laugh because here's the, here's the next, right? So yes, exactly. This is called the Wronski problem. And classically, it was exactly rational, like it wasn't about curves. Classically, the Wronski problem was find rational functions with a specific set of critical points. And I mean, in this case, you could basically work it out. It wasn't so hard to find that example. But we're also going to think more generally about having a curve in space with specified flexes instead of just critical points. So that's the Wronski problem.
Can I ask a stupid question?
Lots of questions.
From a couple slides ago, what did you mean by the tangent plane of the curve?
I mean the plane spanned by phi of t, phi prime of t, phi double prime of t. That's one way of putting it. And even though these quantities depend on the parameterization, the plane that they create does not.
Gotcha, thanks.
Yeah, it's also the unique plane that meets the curve to order more than 2, or something like that. I mean, there's some unique, yeah, there's a unique plane and it has some multiplicity of intersection with the curve.
Cool. Thank you.
Okay, so basic question, how many curves have a given Wronskian? First question we ask about any geometry problem. And it turns out, and this is just sort of classical algebraic geometry dating back to probably the 1800s, that if you fix all of the t values, and you prescribe all the flexes, then there are only finitely many parametric curves that have that specific Wronskian. And here I should say this is up to projective coordinate change. So if I'm just writing down the same curve but in different ambient coordinates, then I'd have infinitely many. So we're not going to count that. So this is there's finitely many up to projective change of coordinates. Okay, and actually more is true. There's a deep connection here to Schubert calculus. And I'm going to say more about this later. So I'm not going to define exactly what standard Young tableaux are, except to say that the number of such curves, and here you have to count with multiplicity over the complex numbers, it's given by some kind of interesting combinatorial set, the set of standard Young tableaux. So we'll come back to it later. I'll tell you in a few more slides what the connection to Schubert calculus is. But first, I want to tell you, I think I can now tell you the statement of the Shapiro-Shapiro conjecture, which has to do with this real and complex number stuff. So what happens if you look at this problem over the real numbers? So this is the Shapiro-Shapiro conjecture, which dates back to the 90s. It's actually a theorem now due to Mukin, Tarasov, and Barchenko in 2005. And they proved a stronger form of it in 2009. So here's what it says. If the Wronskian has all real roots, so all the flexes are at real t values, then phi itself is defined over R. So that means up to changing coordinates, we can write down our curve using real polynomials. And I want to say just how incredibly unusual this is as a geometry problem, because once you specify the Wronskian, finding phi involves solving a bunch of equations to make the Wronskian be what we wrote down. And typically when you solve real polynomial equations, you get a mixture of real and complex conjugate pair solutions. You would never expect to just get all real solutions. And so when this was noticed in the 90s, it just got a ton of attention. It's extremely unusual to find a real algebraic geometry problem with real solutions. And I'm not going to tell you anything at the moment about how this theorem was proven, but I do want to tell you where we're going today. So this is the theorem that Kevin and I proved last year, which generalizes. So instead of having all real roots, we're going to allow the Wronskian to have any mixture of some distinct real roots and some complex conjugate pairs of roots. So and we count how many we have. So all possible ways of having basically a Wronskian that's a real polynomial, but it may have complex conjugate pairs of roots. And I'm going to come back to the exact theorem statement later, so you don't have to really absorb it yet. But I'll say that there turns out to be this cool connection to the representation theory of the symmetric group. And so you don't have to absorb it yet. I will say that part of what's cool about this theorem is that it actually generalizes the Shapiro-Shapiro conjecture. So in the case where N2, the number of complex conjugate pairs is 0, this will turn out to recover the Shapiro-Shapiro conjecture. So that's where we're headed. We're going to be looking at Wronskians with real and complex conjugate roots. Okay. Cool. We'll actually come back to these theorem statements 2 more times in this talk. So it really is okay if you didn't, absorb all the details of it yet. Okay. So I hinted at this connection to Schubert calculus. So the first big thing we need to do is talk about Schubert calculus. So we're going to be looking at, so Schubert calculus for the purpose of this talk will mean geometry, and specifically enumerative geometry about planes. So we're going to be working with the algebraic variety called the Grassmannian, which is the space of planes of a given dimension in a vector space. So here GRKN means the set of all vector subspaces of Cn with a fixed dimension. And so this is an algebraic variety. And so people look at Grassmannians in every vector space you can think of. For us, we're going to be thinking about the space of polynomials, degree at most n. So this is, I guess this is Cn plus 1. And we'll be looking at subspaces of the vector space of polynomials. So that's going to be our Grassmannian. Okay, so Schubert calculus, which is named after Schubert, whose first name I don't know offhand. Is it like Hermann? Anyway, well, so Schubert varieties are also named after him. And so they involve geometric conditions about planes. And so I've written down the simplest kind of Schubert variety. So here, let's look at how this definition works. So we pick an n minus k dimensional plane, so kind of a complementary plane. And we look at the intersection between our subspace of dimension k and our complementary dimension space of dimension n minus k. And if you think about linear algebra, typically a k-plane and an n minus k plane in Cn will be linearly disjoint. So they'll only meet at 0. And so the condition that we'll impose is that that should not happen. And we instead want our k-plane and our complementary plane to touch, or we want the k-plane to touch the n minus k-plane. And so this is like this is an incidence condition. It's saying that a certain determinant is 0. And it turns out to actually be the lightest condition that you can impose on a k-dimensional plane to say that it just manages to touch a specified complementary plane. So this is actually a codimension 1 subset of the Grassmannian. So it's called the Schubert variety. This is actually the only Schubert variety we'll need, but it's still nice to have some context here. So in general, we don't just look at a single complementary plane, but for Schubert varieties, we look at a whole complete flag of nested subspaces of Cn, and we look at how S, our subspace, intersects each part of the flag, and we specify some amount of intersection. And in the setting we're in with polynomials, we have these specific kinds of flags that I'm going to call divisibility flags. So we fix a complex number, z, and our flag consists of, first we take all the polynomials that have a root at z, so divisible by t minus z. Then the next smaller step is polynomials divisible by t minus z squared, and then t minus z cubed, and so on. And so that would be our flag. And so there's some more general version of this problem that would involve looking at, Schubert varieties with respect to these flags. So this is all about roots of polynomials in the end. Okay, questions so far?
Yeah, this last divisibility flag, what space are you in?
This is in our vector space of polynomials. Yeah, thank you. So we're always going to be thinking about the vector space of polynomials at bounded degree. And so this is our flag.
Oh, I see. I just missed that. Sorry.
Cool. So this is how we talk about planes. And so how does this connect to Wronskians? So I put the definition of the Wronskian back up. It's this determinant where we have f0 through fk, and then their derivatives and second derivatives and so on. And I claim that up to scalar, the Wronskian only depends on the subspace spanned by f0 through fk inside of this vector space. It doesn't depend on the individual polynomials. And the way to think of that is that if we, if we changed basis on our subspace, so for example, if we switched f0 and f1 in our subspace, then we would be doing a column operation on this matrix. And or if we added f0 to f1, we'd be doing a column operation. So the determinant, the Wronskian, would only change up to a constant multiplier. So that means that up to scalar, we're getting the same Wronskian. So the way to think of this geometrically is that this gives us a map of varieties from the Grassmannian of subspaces of polynomials to the projective space of polynomials, where we take our subspace, we calculate its Wronskian, and then we forget about the leading coefficient. We're just going to remember the roots of the Wronskian. That's basically what it means to have a polynomial in one variable up to scalar. Okay. So the Wronski map is encoded in this map of varieties. That's what the Wronski map is. And it's nice to think about fibers of this map in the context of the Wronski problem. So what is a fiber? We fix a point here. We fix, we fix what our Wronskian is up to scalar. Fiber means looking at everything that maps to it. What are all of the phi, all of our collections of polynomials upstairs that have that specified Wronskian? So a fiber of the Wronski map is literally a set of, well, the set of maps phi whose Wronskian is specified. We specify the Wronskian. And concretely, just to remind you how this all works, this means it's the set of maps of curves that have, say, T1 through Tn as the specified set of flexes of the curve. Okay, so this lets us, okay, with all of this setup, what the bottom line is that this means that we can formulate the Wronski problem, not just as, find all the curves in some hands-off way, but in terms of this map of varieties, where we're trying to understand fibers of the Wronski map. We fix the Wronskian and we look at the fiber. Okay. So now here's where Schubert calculus comes in. And this is just very cool. So let's say that we fix our Wronskian and we look at the fiber over it. So I claim that that's an intersection of Schubert varieties. And it comes down to this fact, which is that it turns out, and I'm not going to prove this, but it's like a pretty nice algebraic calculation. The Wronskian having a root at a specific t value is equivalent to phi being inside of the corresponding Schubert variety. It means that basically our space f0 through fk has some element g that has t minus ti to high order, divisible by something like t minus ti to the n minus k, or something like that. If you sound this out, you can exactly figure out why this is going to correspond to having a flex in the curve. So that's for one root. Here we're looking at a fiber where we've fixed all of the roots. So a point in this fiber is in the intersection of the corresponding Schubert varieties, because we've said what all of the roots are. And so in enumerative geometry and in Schubert calculus, intersecting Schubert varieties is exactly the thing that, that we have a bunch of tools to do. There's tools from Schubert calculus that exactly tell us what happens when you intersect a bunch of Schubert varieties and count how many points you get. And so here it turns out that this is like one of the first calculations you would do if you were learning Schubert calculus, would be to show that an intersection of this form, a complete intersection of Schubert codimension 1 Schubert varieties, is given by the set of standard Young tableau of this shape. And I'll actually make this a bit precise here. We draw a rectangle of size k+1 and width, height k+1 and width n minus k. And we fill it with the numbers 1, 2, 3, and so on, 1, 2, 3, 4, 5. And the only requirement is that from left to right, each row of our diagram needs to be increasing. And if we go down any particular column, each column needs to be increasing. So you can kind of see that here, that from left to right and down a column, these numbers are increasing. So you can see that there's a lot of ways to do this. And there's like a formula, there's the hook length formula, which says some product of factorials counts this set. But I'd actually say that the formula is sort of beside the point here. Like really, there is some interesting combinatorial model for this problem. And what we would hope is that the combinatorial properties of this set, whatever they are, recursive structure or something, are reflected in the geometry of this problem. And that's where we're going next. Okay.
Can I ask one thing before we go on? I don't know if you're going to get to this, but so you're only intersecting one box Schubert varieties for this. Do the sort of bigger partition Schubert varieties correspond to anything naturally in the Wronskian?
Yeah, so they correspond to having, there are parts of the fibers if you have repeated roots. So implicitly here I've been using distinct roots, but if you have repeated roots, then you'll be getting other Schubert varieties.
Cool.
Okay. All right, so let's look back at the theorem statement, the Shapiro-Shapiro conjecture. And here I'm stating it now in terms of the Wronski map. So if the Wronskian has all real roots, then the fiber is reduced and every point in it is real. So this is partly just saying what I told you before. If every flex of the curve is real, then the point, as the point in the Grassmannian, is a real point. That means that we can find a basis for that subspace consisting of real polynomials. Okay, but actually I told you that they proved something stronger. And so they also proved that the fiber is reduced. And so here, oh, I guess I didn't really draw attention to this, but of course you have to count with multiplicity when you're doing enumerative geometry. And so part of what's so unusual about this problem is that, so the fiber being reduced means that all the points in the fiber have multiplicity 1. It means that this intersection is a transverse intersection, so no multiplicities. And so it means that actually, like, the first big consequence is that the cardinality of the fiber is exactly the number of standard Young tableau. There's never any multiplicity. And this is also just super weird, completely unheard of in algebraic geometry, because we would normally expect that most instances of a problem, maybe most choices of Wronskian, would give us a reduced fiber, but that there would be some where you have to count with multiplicity. And instead, that just never happens in this problem. And so, okay, I mean, if you were looking at this from the perspective of combinatorics, then you should think, okay, well, we always have exactly a number of solutions equal to the number of standard Young tableau. And so actually Kevin Prabhu 10 years ago, showed that each point in the fiber can be labeled canonically by a standard Young tableau. And then there's been a whole bunch of other work since then, since this reduced statement is saying that points in the fiber can't collide with each other because that would introduce multiplicity. So there's also an interpretation saying that covering spaces of the moduli space of curves have to exist. And then a bunch of other stuff, including things that Maria and I worked on back when we were in grad school and a little bit more since then, looking at a version of this problem where the fiber is one-dimensional. And so the fiber is a curve instead of a finite set of points. And we looked at the topology of this curve. No, I won't say more about that. Yeah.
Can I ask a question?
Yeah.
So are there like, is this reducedness, okay, so what I'm asking is like, could there be conditions on the Wronskian of phi that are weaker in which the fiber is still reduced, but maybe the points aren't real? Or the fiber is known to be reduced?
Yeah.
Isn't that the weaker version by like Eisenbud and people?
Yeah, I mean, so most points. Offhand, I don't know of another. I mean, so certain. Yeah, offhand, I don't really know much of what to say, except that most points in the Wronski map have reduced fibers by some genericity statement.
Yeah.
Wait, is there another, can I maybe follow up from that? Is there a way of, isn't there the theorem of like, even if you don't pick real points on, like in the way we used to say it in terms of like osculating flags, if you don't pick real points, but you still take osculating flags, don't you know that that fiber is, that it's a transverse intersection? So then could you transfer that back to the Wronski picture?
The Wronski,
right? And then it wouldn't be real, but it would be.
Finite. Yeah, always finite, but it doesn't need to be reduced in general.
Oh, I see.
Sorry, since we stopped your momentum a little bit, I have a question too.
Yeah.
So from, you talked about taking sort of n distinct roots, right? And so it seems like this way you're kind of getting a covering of M0n of R, right? So what is entailed into extending this to M0n bar? Is that?
Yeah, a lot of like fascinating geometry, and I think I just like can't even afford to get into it, except that it's like a really cool picture. Yeah.
Cool.
Okay, actually I want to zoom in on this very first consequence about identifying points in the fiber with Tableau and show you how that works, because I think that this is just cool. So this is a kind of a general idea. How do you find combinatorial information in a geometry problem? And so we're going to take our Wronski problem and we're going to degenerate it on purpose and make it break into pieces. And so this is not unique to this problem, or even to enumerative geometry. In birational geometry, people also have these sorts of degenerations in mind. And so this is a very broad idea. So here's how it works in this case. So we're gonna look at the version of this problem where the roots are a tuple of this form, where we can fix for some z in C, and let's say that z is not 0. Okay, and so we're going to take the roots to be z, z squared, z cubed, and so on. And we're going to take the limit as z approaches 0. So we are deliberately making all of the roots go to 0, the same single repeated root n times. And so this is definitely breaking the problem, because the way I've described it up until now, in the limit, we would be intersecting the same Schubert variety n times. So that, of course, that's not what's going to happen. But something about the problem is going to kind of break and transform in the limit. And so we want to know what happens to the fiber. Okay, so I want to illustrate this with an example, and the example is cubic rational functions, because this one is kind of small enough to write down. So this is hearkening back to the beginning of the talk. Degree 3 maps from P1 to P1. So such a map is given by writing out a ratio of 2 cubic polynomials, and you can just put those coefficients into a 2x4 matrix. And so it turns out, so we're taking the roots of our Wronskian and letting them approach 0. So it turns out that we can work in an open subset of the Grassmannian. This whole bit of geometry is going to work in an open subset where, for simplicity, I picked this one, where you can simplify the matrix to this form. So it just corresponds to doing some rearrangement of the coefficients to make the function look like t squared over t cubed. Okay, so here's how this problem goes. So numerology, there's 4 roots. So just like there was plus or minus 1 and plus or minus I in the earlier example, so 4 roots. The fiber is counted by standard Young tableau of shape 2 by 2, and there's just 2 of them. So there's going to be 2 points in the fiber. And so here is a kind of schematic picture of what's happening. Our roots are at z, z squared, z cubed, and z to the 4th. So they're all going to 0. They're kind of going to 0 at different speeds. So they're not like the z to the, I don't know, one of them is getting there faster than the others, probably z to the 4th. And so as z approaches 0, we have our 2 points in the Grassmannian, and they are converging to some limit. And it turns out that if you solve for the points, and so here I'm imagining solving for the points and writing out maybe a power series representation to see what the actual matrix is. And because it turns out that, first of all the entries of the matrix are going to 0. As z approaches 0, but they're going to 0 at different rates. And so I've written out kind of the order of vanishing here, and I want to stress these 2 exponents. So it turns out that one of the points will have a z cubed and a z to the 4th, and the other one will have a z to the 4th and a z cubed. And using that data, these order of vanishing information, we are able to give one label to one point and one label to the other point. Okay, and I've said this very informally. I haven't really spelled out to you how exactly the labeling system works. There's some picture that we make. We write out this limiting matrix. In general, we don't just look at the entries of the matrix, but also all the minors of every size of this part of the matrix. We write out all their orders of vanishing, and that just spells out a standard Young tableau for you. And I'm happy to say more about the details here after the talk if you're curious. But I want to just say, the point is we have this procedure. It spells out a bunch of standard Young tableau, and it gives a bijection. This is what Kevin proved and David Spire proved in the moduli space of curves context. A bijection between the limiting fiber and the set of standard Young tableau. Okay, and not only that, here's a consequence. So by the MTV theorem, the Shapiro-Shapiro conjecture, we can take our limiting labels, we can take the labels we've come up with in the limit, and we can kind of track them back to the point, to any other fiber. And so I want to just rewind to the picture. So here the idea is that this point is labeled by this tableau, and this point is labeled by this tableau. So the way that we label any other point, so according to the MTV theorem, points in the fiber cannot collide with each other. That would introduce multiplicity. And so they have to stay separate. So we just rewind and we say that this point and this point have the labels that they would have gotten in the limit. And so from that, we can just sort of, we use MTV as a black box, doesn't matter how it's proven, and it lets us pull these limiting labels back to the rest of the Wronski map.
Sorry, can I ask a question? Sorry about my obsession with M0N bar, but it seems to me that right now you've actually sort of gone to a deepest stratum, a zero-dimensional stratum of M0N bar, and showed to me that you can actually define your fibers there. Is that right?
Yes.
Okay.
That's right. That's right. We've gone to exactly this stratum of M0N bar.
Cool.
Yeah. Yeah, the translation between those pictures is very cool. Okay, and there's more. I mean, so here I've had all of my points be like I haven't allowed roots to be at infinity, whatever that means. But if you do allow roots to be at infinity, then you can do more things. You can sweep one of the roots around infinity, and that turns out to transform the bijection. And it's all according to these well-known combinatorial bijections in Schubert calculus, like standard tableau promotion, standard tableau evacuation, and then like there's been all this other work since then. So here I've mentioned some of the stuff Maria and I worked on, where you discover other things from tableau combinatorics in the explicit geometry of this map.
Can I actually ask one?
Yeah.
I realized I never asked myself, are Prabhu's and Spire's labelings, do they actually coincide? Are they the same bijection?
Yeah.
Okay.
Yeah.
But Spire came up with his a totally different way, right? Through like wall crossing.
Basically the same idea. I mean, yeah,
okay.
Basically the same idea. He had to figure out how to sort of formally construct the limiting fibers.
Mm-hmm.
Yeah. Okay. Cool. So now I haven't told you at all about how the MTV theorem worked. And the reason for that is kind of a sad thing, which is that it turns out that this geometry problem was solved using techniques that really don't have anything to do with geometry. So the beta ansatz, which is actually from quantum mechanics, and is a kind of like, I don't know, it has to do with operator theory and integrable systems. And I mean, basically like every single theorem I referenced on the previous page uses this MTV theorem as a black box. We don't need to know how it's proven. That still turns out to be good enough to do all of this beautiful geometry afterwards. But there's still questions that people would like to know how to do. For example, what if you stop saying real roots and start allowing things like complex conjugate roots? And so there's been kind of interest in going back and replacing, or at least finding a new approach that, that treats this geometry problem using actual algebraic geometry. So that's what I want to talk about next. So this is going to be looking at, instead of having real roots, we're going to allow mixtures of real and complex conjugate pairs of roots. Okay, so here's how we do that. So, okay, I have a bunch of notation here. Basically, we go to our space of real polynomials and we cut it up every possible way. So we specify a partition of 2s and 1s. So this just means we say we have some number of 2s, some number of 1s, and we will consider the set P of mu polynomials with our specified number of real roots, distinct real roots, and specified number of complex conjugate pairs. And these kind of decomposes the space of polynomials of degree n into these chunks. Okay, and as a base case, if the case of all 1s corresponds to all real roots. So we're going to kind of cut up the Wronski map, and we're going to look at, so the restricted Wronski map, where we look at just what's going on over one of these cells, where we specify one type of real polynomial, and we look at what's going on in the Wronski map. And so if you are super comfortable with Schubert calculus, I'll remind you that we're always in this Schubert cell, since none of the roots can be at infinity. So our picture is always going to be affine space upstairs, mapping to affine space downstairs. Okay. Cool. So here's the question we want to answer. How many real points are there in the fiber? And it turns out that they're not all, that in general, they will not all be real anymore. That was really special for the Shapiro conjecture. So there's just going to be an upper bound and a lower bound. So the upper bound is this number, the standard Young tableau that I mentioned earlier. This is the algebraic degree of the map. It means the number of points over the complex numbers counted with multiplicity. So in the best possible case, those points could all be real and they could all have multiplicity 1. And in that case, that would be the count of the fiber. Otherwise, it's just an upper bound. Okay, so that's the upper bound. And then we have a lower bound, and the lower bound actually really uses real algebraic geometry. It's going to use something called the topological degree of the map. So I want to illustrate this by way of a picture. So I've drawn kind of a toy pretend version of the Wronski map here. I've tried to make it look like a cubic curve. So you can imagine here that the algebraic degree is 3, a cubic curve. So all the fibers are 3 points over the complex numbers, but you can see that some of these fibers have only 1 point. So for the topological degree, what we do is first we have to orient both spaces. So I've drawn these arrows along the base and along the top. So we picked some orientations. And now we count all the points with plus or minus signs. And the plus or minus sign depends on whether the orientation is the same or different from the orientation at the base. So that point has a plus because it's the same way. In the middle, we have a plus, a minus, and a plus. And over here, we have a plus. And you will notice that if you add those all up, you get plus minus plus equals 1 plus 1. And so this number, this plus or minus sign count, is a fiber invariant. And it is the topological degree of this map. Okay, and it turns out that you can calculate it from any fiber, which is very useful because we're going to do our limiting procedure and go to a specific choice of fiber. Okay, and there's one important idea here that's going to make this all work. So in this picture, I said you have to choose an orientation. Usually this is not really important because if you're working on a connected manifold, then there's only 2 choices of orientation, forwards and backwards. And, but in this case, we've kind of cut up our space into a lot of pieces. So in general, upstairs, there's many connected components. And so there's something like 2 to the k, 2 to some power of 2 number of choices here. And we're going to use a very specific choice called the character orientation. And this is where things connect to the representation theory of the symmetric group. So I'm going to tell you the theorem statement. And so here, okay, so here I put up the character table of S4. Symmetric group on 4 elements. You might have calculated this in a representation theory class sometime. So up here, we have the conjugacy classes on S4. And over here, we have the Young diagrams with 4 boxes. And so we're going to be zooming in on the rectangular Young diagram. And we're only going to consider conjugacy classes of 2s and 1s. So these are like the cycle type of our partition. So remembering that a 2 is going to mean a complex conjugate pair of roots, and a 1 is going to be a real root. And now the theorem statement is that using character orientation, the topological degree of the restricted Wronski map is that character value. So it would be 2, 0, or 2 in this part of the chart. Oh, and I left out, okay, I have to rewind one step here. I forgot to say the most important thing. I said this was a lower bound. So let's say the topological degree was 5. Well, that means if you add up all the plus and minus signs, you get 5. So you must have had at least 5 points, since there could be cancellation. So the topological degree gives a lower bound on the total number of real points in the fiber. So those numbers I had on the chart on the next page are lower bounds for so 2, 0, and 2. You can see that in this case, there's not really a useful lower bound. It could be 0 for different instances of the problem.
Sorry, did you define the character orientation? Like, what do you do with these numbers?
Yeah, so actually, hold that thought for a moment because I will define it, but I want to just show you first, how does this lead to the Shapiro-Shapiro conjecture? And also, what is this character? Because I will come back to it, but in order for it to make sense, I have to tell you something about these characters. Yeah, so there's actually many formulas for calculating the characters of the symmetric group. The one that's most relevant to us is called the Murnaghan-Nakayama rule. So here's how it works. We look at tableau, so we have our partition mu, 2s and 1s. We have our rectangle, And so we fill our rectangle with a sequence of dominoes and squares. And so each of these is required to give a domino, and this one is required to give a square. We fill in, we consider all possible ways to fill in the rectangle. And then we count with plus and minus signs. And the rule is that a vertical domino is a minus sign. And so we have to put those all together. Each vertical domino gives a minus sign. And so we add up all of the tableau this way. And that's the formula for the characters of the symmetric group. So now let's look at what happens in the special case where all the roots are real. So mu is all ones. There are no dominoes in our picture. And so all that we're counting is with the plus sign, every possible standard Young tableau. So in this case, our lower bound, which is this Monohau-Nakayama rule, equals our upper bound of the number of standard Young tableau. And so that tells us that every point in the fiber is real. And so that's the Shapiro-Shapiro conjecture. So that's sort of how this fits into the context. But of course, in general, we just have some other lower bound, and it's whatever these characters of symmetric group representations are. Okay, so now to Maria's question. So now with the time I have left, about 10 minutes left, I just want to show you pictures of how all of this geometry comes together, starting with this question of what is the character orientation? Because there is a standard orientation upstairs and downstairs. I said earlier that we're kind of working in an affine chart, which is an affine space. So it has a standard orientation, and the downstairs has a standard orientation, and that one is bad. That one was actually studied something like 15 years ago. It turns out that with that orientation, the degree is always 0 or 1 or -1, according to like a parity thing. So it's just never a useful, even in the case where it's 1, it's always obvious that you would have had at least 1 point because some polynomial had odd degree. And so there's no exciting information to have here. So we're going to change the orientation, and it has to do with looking at these different regions. So we're going to look at different P of mu's. So I've kind of put together a diagram here where we have 2 real points, and we bring them together and then pop them apart into 2 complex conjugate points. So we have C and C bar point over here. And over here we have a collision, so where the discriminant, basically the discriminant of the Wronskian is 0. The Wronskian has a repeated root. Okay, and so now we're going to look upstairs in the fiber, and something, I have to delete this to make room for the text, but something interesting happens. So in terms of curves, basically we get 2 things upstairs, and this is because I don't know, you can think that in terms of curves, we had 2 simple flexes that come together into a double flex, and there's 2 different ways that that could happen. You could have a rank deficiency earlier or later in terms of the derivatives of the curve. I sort of feel like the geometry of curves is kind of fading into the background here. Really what's happening is that there are 2 codimension 2 Schubert varieties. One of them is a vertical domino, and one is a horizontal domino. Schubert codimension 2 Schubert varieties. And so they make these kind of walls that we're crossing upstairs in the picture. And so we're going to take, let me erase we're going to take this one, the vertical domino, and we're going to multiply through, we're going to take our standard orientation and multiply by the equation of this vertical domino wall, which is a union of codimension 2 Schubert variety. So it is a divisor. It has a global equation, and we're multiplying. So concretely, what that means is that upstairs, if we cross this way, we're crossing the vertical domino, and we get a minus sign. And if we are in the other part, we cross the other one, and we don't get a minus sign. So this is going to connect us to the representation theory, because we want vertical dominoes to count as minus signs. Okay, so that's how the character orientation works. We just kind of artificially flipped everything every time we cross the vertical domino walls. Okay, and now, so here's the sketch. This is, so the claim is that this topological degree equals this character value from the symmetric group. So topological degree is a fiber invariant. So we can go to any fiber to calculate it. And not all the fibers are the same. And we saw in that picture, fibers can look different from each other. So we have to pick a good fiber. And so we're going to go to the same limit that I drew for you a while ago. We're going to let all the points go to, all the Wronskian roots go to 0, a bit of stuff about complex numbers. The point is we're going to go to a limiting fiber. And we're going to use exactly the setup that Kevin gave. So I feel like I'm being too casual here. We use a slightly modified version of what I showed you earlier in order to account for complex conjugate pairs. But apart from that, we're using stuff that Kevin did 10 years ago. We go to a limiting fiber. We already know how to label points in that fiber by tableau. So you can imagine that over in the middle, we have fibers we don't understand, but on the edges, we have fibers that are labeled by tableau. And then what we do is we connect up all the tableau to each other, and we see how the signs change along the paths. So concretely, let me give you an example. So here I've drawn, there's 2 cases we have to look at. So here I've drawn the case where the box number 1 and the box number 2 get joined together into a vertical or horizontal domino. So that corresponds to saying that T1 and T2 are starting out as real numbers, and then we're passing to T1 equals T2, and then T1 equals T2 bar, complex numbers. And we show that upstairs in our combinatorial picture, there exists a path that connects this tableau to that tableau, which crosses through this sign changing wall. And therefore, the orientation of the right-hand tableau is the opposite of the orientation of the left-hand tableau. So this is showing that introducing a vertical domino gives a minus sign. It changes the orientation of that point. So this point and this point have different orientations. And we also show that if you start at this point, then there is a path that connects it over to the point labeled by that same tableau, but with the horizontal domino. And this time the path travels through the part of the map with no sign changes. So that implies that the orientation at this point is the same as the orientation at the starting point. So we're just kind of like drawing these paths and saying, okay, the orientation doesn't change, the orientation does change. And we're getting from it that introducing a horizontal domino does not change the orientation, but introducing a vertical domino does change the orientation. Okay, that's actually like half the theorem. The other half of the theorem is what about points that are not adjacent to each other? So we have to show that there's no sign change if you take 2 boxes that are not adjacent to each other and you switch them. That would be enough to finish. Then we have enough paths to connect every tableau to every other tableau. And so this is just crazy. So we draw this degeneration here, and it turns out that you can make a loop that starts at here's 2 and 3, and here's 2 and 3, same tableau, but with the labeling switched. So we show that you can take those 2 points in the fiber and connect them by a kind of U-shaped path like this. And if you look at what's happening, we cross, so we have kind of an empty fiber over on the side. And that's, so we have something that looks like a parabola. And so there's 2 sign changes. Over here, we cross through the vertical domino variety. And so that's the one where we get a sign change. Over here, the path turns back. And so by topology, we get a sign change. Just by like plain old, the path is backwards. So here we get a second sign change. And then on the way back, we cross through the other variety and there's no sign change. And so all in all, we have the same sign as we started with. And so these points have the same orientation. And so that tells us that switching 2 boxes that were not adjacent, those points must have the same orientation in our map. Okay, so with all of that together, we've connected up all of our labeled points. We've shown that they have the same plus and minus signs, the same orientations, according to what the Moynihan-Nakayama rule predicts. And therefore, the total count equals this character value of the symmetric group. So that's the end of the proof. Yeah. Okay. I mean, that's the picture. These basically like showing these two diagrams that I've drawn for you and constructing the character representation are really like the core of what we did. Okay, so I'll just end by pointing out that there's a bunch of interesting follow-up questions here. So first of all, here I've only talked about character values with 2s and 1s. This is because a 2 was a complex conjugate pair, and a 1 is a real point. So we had this like very specific interpretation, but it's still like a natural question. What about all the other character values of the symmetric group? I will say that the rectangular partition, we were even doing this, chi rectangle of mu. So there is a generalization of this problem to allow 1 or 2 extra Schubert conditions that are not codimension 1, and so you can get other characters. You can replace this by a different shape, but we still only really know how to make sense of those conjugacy classes. So anyway, so there's all these other character values. It would be interesting to see if they occur as topological degrees of some part of the Wronski maps geometry. Okay, the next one is that we've generalized to looking at these cells P of mu, where the restricted Wronski map over these loci other than the locus of having all real roots. And so there's some kind of folding that's happening there. This may be very hard, but I would be very interested to know what the explicit geometry looks like. And ideally, I mean something like a combinatorial cell decomposition of this part of the Wronski map with labels telling us how all the pieces are attached to each other. Because that's what we have in the full Wronski map picture with these diagrams. Okay, and then the last one is about this whole parallel story that I think there's probably a lot of interest in at CSU because you guys are really into stable curves, and as I could tell from Renzo asking about it. But yeah, there's a whole parallel story here about M0 and bar, and there's like a whole other version of this talk that I could have given talking about M0 and bar. And so how does the geometry work there? And really, I mean the new geometry, because the case of all real roots is David Speyer's theorem, and it's fully understood. It's very intricate. It's very cool. But this modified real structure is not known. And I'll point out this like very bizarre fact that I don't have an explanation for, which is that the core new idea here that we had, because Kevin had already come up with domino tableau labeling 10 years ago. The orientation is really the new thing, how to get these plus and minus signs. And but then, like in fact, we actually use M0 and bar in our proof because we have to make sense of these degenerations along the boundary. But if you know M0 and bar over the reals, then it's not an orientable manifold. So, well, yeah. So that's kind of weird. I'm not really sure what to make of that. It would be interesting to understand what this character orientation, which for us is only defined on the Wronski map, but which we analyze using stable curves, like what does it mean in the stable curves? So anyway, that's just sort of a mystery. Okay, and that's it.
Right.
Oh, thank you all.
Yes. People can unmute themselves to ask questions or just clap or have emojis. I'm gonna get, well, people are muting themselves. I'm gonna get started with my question, which is, so you said, so David Speyer worked out the covering of M bar 0 n over the reals.
Yes.
And so over the complex numbers, is it not worked out because it's more difficult or because it's less interesting or both?
So the thing that is worked out over the complex numbers is that there is a proper flat family that extends, that sort of is kind of birational to the Wronski map, over that transforms the base so that instead of being the projective space of C, so the Wronski problem makes sense over this vector space of polynomials.
Mm-hmm. Yeah.
This is birational to M0 and minus 3 bar.
Mm-hmm. Yeah.
And we have the Grassmannian up here, k plus 1. And this is birational to curly S box to the k n minus k by David Speyer. The S is for Schubert, not Speyer. And so this is some generalization of an intersection of Schubert varieties. And so this is also, and so there's some kind of commuting diagram here. And so this picture makes sense over C. And this is flat. Oh, uh-oh. Okay, this is flat, and sorry, my iPad was misbehaving. Flat is Cohen-Macaulay and is proper. So there is a like fully understood algebraic picture. What's not understood is things like the explicit topology. If you try to look at complex points in this map, they can have multiplicity. There's like no good.
Do we know where it branches and what the branching ordering is, or no? Okay.
Maybe in small cases, yeah. And we know how it looks over R. Over R, we have a picture that's just as explicit as the one that I sketched for the Wronski map. And there it involves doing flips. You have to somehow modify the definition of standard Young tableau so that when you cross a wall in M0 n bar, where you're introducing one node and you're taking some points, that corresponds to taking a collection of entries in the standard Young tableau and somehow twisting them. Yeah, Maria and I would probably call this evacuation shuffling, which is our term for a closely related operation. Yeah. I can draw you one more picture here if you're curious, Renzo, just to show you how okay, let's stick with green. So here is T1, T2, T3, T4. Mm-hmm. So we have our roots of our Wronskian. And if we degenerate to this limit, where we have T1, T2, Q, T3, T4. Mm-hmm. Then up here, so in the original one, we have an intersection of 4 Schubert varieties, F of Ti. Mm-hmm. In the limiting one, we have 2 separate pictures. We have this one and we have this one. So on this one, T2, T1, Q, we have 3 Schubert conditions. This one is sort of unspecified. And in the other picture, we have T3, T4, and Q. And basically, I mean, this is actually not David's theorem. This is Michel Briand's theorem. Shows that the way that the picture transforms is that you still have a single box here, and a single box here, and a single box here, and a single box here. But you can get every possible Schubert condition at the node. And so you have to understand what happens if you have a different Schubert condition in the node instead of just a single box. And the correspondence is that you simultaneously get a Schubert condition and its complementary Schubert condition at the node. And then this gives you one chunk of the fiber, and you take the union over all of them. And anyway, there's some concrete union of smaller Schubert varieties. It's a recursive definition. It has kind of the same recursive structure that M0 n bar has. The edges being smaller M0 n bars. Here, these Schubert problems become smaller Schubert problems with not as many marked points.
I see. So that, sorry, again, hammer and nail kind of thing, but that is the kind of pictures that remind me of field theories, of topological field theories. Is there any kind of relation?
I don't know.
No. Okay.
I don't know what a topological. I've heard the term, but I don't know what it is. So maybe we could talk about it another time.
Yeah. So.
Yeah. Can I ask other annoying questions? No, not to say any questions were annoying. No, more other annoying questions from me. So the SN action, is there any SN action actually hiding under here that gives you the character? Like, I mean, are there like tabloids of rectangular shape floating around?
Yes. Actually, Sean Griffin asked the same question when I spoke on this at UW. It's a great question. Yeah. At the moment, I don't have any Yeah, I don't understand why we're getting the characters of the symmetric group. I think in a way, like having more than this one instance of it would probably clarify it. But yeah.
Yeah, I mean, it feels like when you were talking about it, it feels like, okay, we have dominoes that give you a sign, and that happens to be a special case of the Murnaga-Nakayama rule. But I wonder if the general thing that you're looking for like more different, not just complex conjugate pairs, say, wouldn't actually be the Murnaga-Nakayama rule, but it would be some other generalized domino tableau thing, you know?
Oh, I see.
So that's why I'm wondering, like, if there's an SN action somewhere, then yeah, I believe that, you know, maybe there's some SN thing going on. I don't know. I'm just sort of throwing in ideas that kind of came to my head.
One variety that has an SN action is M0 and bar. So maybe
that's true.
There's something going on there.
That's true. That's true. And I guess there could be copies of the rectangle representation for some reason. I mean, I don't know what that would have to do with the Wronski map, but it's pretty intriguing.
I'm not sure. I don't know off the top of my head. This is like, maybe there's a simple answer to this that I'm just not aware of. What is the situation where a character, which is the trace of a representation, occurs as a sum of points? Like, is it a sum of eigenvectors? And you know what I mean? I just like, I don't even know what the right framework would be to have this as a consequence, because what vector space would we be working on?
Right.
So.
Yeah, that's interesting. And can I ask one tiny minor question? If you go back a few slides, there was this thing where you were showing how if you go like around the loop, then you like switch the 2 and the 3. No, it wasn't that many slides back. Like right near the end, just a couple of slides back. Like this one. Yeah. Where you did this thing where you like do the domino thing and then you go around and actually plus changes back to plus when you switch the 2 and the 3. So that felt to me like those Bender-Knuth relations and like the equivalents that we've already had from like the wall crossing picture. Is that basically actually the same idea? Yeah.
So you can tell the reason that the horizontal domino is on the upper branch and this is really for experts. So everyone else should cover their ears. But Maria, it's because here, if you look at the relative position of the 2 and the 3, this is standard. This is like rectification equivalent to 2, 3. And over here, 2, 3 rectifies to 2, 3. So that's why those are the local.
Right.
Which one we hit first.
Cool. Thanks.
Yeah, and then everything on this side of the wall has some complex number magic that's happening, and so it's not stuff that we've previously seen.
I have a quick question, if that's okay. I stepped away for a minute. I think right as Renzo asked a question, but on the last slide when was that Spire's identification of like the kind of the gluing axiom on the M0N, where you break apart into 2 different?
You mean the thing where I started saying what's going on at the node?
Yeah, and you have to consider all possible tableau conditions on the queue. Yeah.
Yeah, it's not Spire's. He used it, but it's due to Michel Briand.
Okay.
I mean, I guess Michel Briand proved something, first of all, much more general about general G mod P, parabolic. And he also proved it for something more general than curves. So he did a degeneration of the diagonal. So of the Grassmannian inside of the Grassmannian cross itself as a union of products of Schubert varieties of all complementary pairs. You can go look at it, and then David Spire showed that that this family is the restriction of that one to the rational normal curve, and so I guess he like observed it. It's like 2 lines of his paper. So
awesome. Thank you.
So really is his Briand's result. So.
Okay. Cool.
But then David Spire showed that this pieces together into this cool family over 0 and bar.
Awesome. Thank you.
Are there any more questions for Jake? Guess not. So, well, thank Jake again. There's emojis that you can use if you don't want to mute yourself. But thanks, Jake, for the talk.
Thanks, Jake.
I will put a link to the video on the Fragment seminar website for anybody who wants to go back and look at it. And yeah, that's about it. And you know, hopefully when we're out of quarantine, you can actually visit us in person.
Yes, yes, that would be
A
great.
bunch of fun things to talk about.
Yeah.
Cool.
Thank
All
you.
right. Well, stay safe, everybody.
Thank you.
Cut this out. Okay. Bye.
See you later.